So chapter 5 we'll be studying about electronics. So we will begin this chapter by studying about electrons, and a little bit about electricity and how we can how the movement of the electrons and different ways electrons can move in a circuit. And then, since we're talking about electronics, we'll talk about some of the components that allow electronic equipment to work. Specifically, we'll be learning about diodes and transistors. And what those are, that's what we'll be talking about later. So these are some of the questions that we will be discussing today. Well, not all of it. We will be discussing mostly question number 1 and a little bit of question number 2. Okay, so what are the thermionic emission and cathode rays? Okay, what are those? What are the functions and uses of a semiconductor diode? So you've learned about we've mentioned about semiconductors before, where it's not completely a conductor, where it's not always electricity easily flows through it, but it's not completely an insulator, meaning to say under certain conditions, electricity can flow through it. Right, so we're gonna take a look at how we can use these things in electronic devices. Okay, what are the functions of an NPN transistor or a PNP transistor? So what is a transistor and how to use it, and what's the difference between NPN and PNP transistors? Okay, how does a transistor function in an amplifier circuit? And how does a transistor function as an automatic light controlled switch and a heat controlled switch? So different things. We will not reach transistor today, but this is all related. So these are the 3 topics in this chapter. It's not the longest chapter, but some of the theoretical side of it can be, well, it is very interesting, and it does take a little bit of time for us to understand. Especially, I don't want to rush through the first one, especially because some of the concepts that we have there are actually quite interesting, and I think quite important for us to understand before we continue with the rest of the other 2 topics. Okay. So we'll start with the first one, electron. You know what an electron is. You've studied chemistry. At least I think all of you are taking chemistry. And even if you're not taking chemistry, you do touch on this even in science and even in physics. So an electron is one of the subsets or part of an atom, as you know. And we know that electrons are negatively charged. We know that much. And we know that electricity or current, okay, the flow of current, when we say current, what is actually flowing are electrons, right? When charged particles, when the electrons are free to move in a conductor. So this is we already learned about this before. We complete a circuit, and that circuit allows the electrons to move through. There's a potential difference, and that causes the electrons to flow. Now, here's an interesting question. Can electrons move through a vacuum without a conductor? So what we have done before this in electricity is that we always have the electrons flowing through a conductor, some sort of wire or some other type of metal to flow through. And this question now is, can electrons move through a vacuum without a conductor? So figure 5.1, which is in your textbook, explains the thermionic emission. I'll explain to you what all of this is. And the production of cathode rays in a vacuum using an extra high tension power supply. Right, so this, when I say extra high tension, I checked on the internet to see what is considered extra high tension. It seems to be different for different articles. So one article I read says starting from 5,000 volts or 5 kilovolts to around 30 kilovolts. So really high voltage power supply. Okay. I know this is this picture may not mean much to you, but let's take a look at what we have here. Actually, I'm gonna draw a diagram because the way the picture is drawn in the textbook. It's a little bit hard to see everything because there's some extra lines. This green, this red, and blue lines are not actually part of the circuit. Okay, they are just pointing to other bits of information. So I'm gonna go ahead and draw this on the whiteboard. So the way this thing works, or what you're seeing here in this picture, is what is known as a cathode ray. Let me just. So this is what we call, we're building something called, or we're creating something called a cathode ray. Right? There are several different ways to do it. There are several different ways to create a cathode ray. This is a cathode ray. This is just one possible way to do it. But I'm going to go and draw it on the whiteboard to make it clear. So you begin with, well, first you have here is the power supply. So we have the EHT, extra high tension power supply. So this power supply supplies the circuit with a high voltage, maybe around at least several hundred volts or more. And we have, of course, we have the negative side and the positive side. So pay attention to where's the negative side and the positive side. In this case, it does matter a lot. Where's the negative and where's the positive? All right. Now, here we have the cathode. And of course, on the other side, of course, we have the anode. Right? So we connect these two wires to the cathode and the anode. So normally, this is not a complete circuit. Right? Obviously, because there's no way for the electrons to go from one side to another. Okay, so since this is not a complete circuit, you have two options now. Now, the most common option is to complete the circuit using a wire. You connect something from here to here. But that is not what we're trying to do today. So what we are trying to do today, or at least what people have done, is instead of using a wire to make the electrons move or electrons flow, we want to try to do this. We want to use the electrons, or we want to make the electrons move through a vacuum and move without a conductor. And we can do that using something called thermionic emission. All right. So what is thermionic emission? This is in the textbook, but it's a bit small, so I'm just going to read. So thermionic emission is basically the emission of free electrons from a heated metal surface. So what it means is that, this is saying is that when you, so the red question was correct, meaning to say the red question, the answer to this question just now, can an electron move through a vacuum without a conductor? The answer is yes, it can. And probably you already thought it's possible because I wouldn't ask it unless it's possible, right? Anyway, thermionic emission is the emission of free electrons from a heated metal surface. So instead of using a conductor, a wire, to give the electrons basically a bridge to move through, we force the electrons. Basically, that's what we're going to do. We're going to make the metal surface so hot that we're basically forcing the electrons to move, or we're forcing the electrons to be free. And then once these electrons are free, they're able to move from one side to another. Now your textbooks does not really explain it in depth. But there are videos. I'm not gonna go into depth, but you can find videos on YouTube that explains when you heat it up. What happens is you're actually adding the amount of energy to that metal surface to some degree, and so that extra energy gives these electrons the freedom or the energy to basically escape from the pull of the nucleus and become a free electron. That's just a very basic explanation of what exactly is happening here. So instead of using a conductor, we're going to use heat. That's why it's called thermionic. It's a combination of two words. So thermal, therma, heat, and ionic or ions. So we're using heat to create ions here. So back to this picture here, and back to the drawing that I have. So, excuse me. So some guy who we were just seeing a video about this guy who discovered the electron. So he decided to do an experiment. So he created this thing. So like I said just now, this circuit is incomplete. So we need to find a way to have it so that we can have the electrons here move from the cathode to the anode. So what we did is we add another circuit. All right. So in the picture, it's not 100% clear, but there are actually two circuits we have here. So now I'm going to draw the other circuit. So now here we have a heating element, usually a tungsten filament. So this heating filament has its own power supply, usually 6 volts. In most of the experiments that are in the textbooks, it's usually a 6-volt power supply. 6 volts power supply. And this whole part here, this whole apparatus here is going to be closed in a vacuum glass tube. Okay, so both the filament, the tungsten filament, tungsten I should say, tungsten filament. So the tungsten filament and the cathode and the anode are both in a vacuum chamber. The fact that it doesn't always have to be a vacuum for this to work, but there's something about a vacuum that's very important that we'll see later. That makes it easier for us to later understand and study these electrons. So when this tungsten filament is connected to a power supply, what happens is, of course, this tungsten filament starts to get hot and hot and hotter and hotter, to the point where when this cathode gets hot enough, this metal plate, I should be clear. The cathode and anode are metal plates. So both sides we have a metal plate. So once this thing gets hot enough, it starts to release electrons. Now electrons, if you remember, electrons have a negative charge. Now because the anode is the positive charge, is connected to the positive side, what happens is now that the electrons are free, they are now naturally being attracted to the anode. And so what happens is we now have a stream of electrons going from the cathode traveling towards the anode. So negatively charged electrons being released and now traveling or being shot towards the positive side, because, opposites always attract, even in science. And that is the basics of what is known as a cathode ray. Now, there are other ways of doing it. There are several different setups that it's possible. I'm just showing the one that's in the textbook. So what is interesting is you've created a situation here where you have what is essentially a pure beam of electrons right here. That is what makes this so interesting, because if you think about it, this means that this is the closest we can get to studying pure electrons. Normally, and like I mentioned before, you can't really study pure electrons because electrons are usually so closely connected with the atom or with the nucleus. So usually you have to study electron as part of a nucleus or part of the atom. But here we have a situation where for a short period of time you have basically a pure beam of electrons. That's why sometimes you'll see the word when you read about cathode rays and these kinds of things. Sometimes you'll see the word electron gun or electron beam. That's what we're talking about here. Oh yeah, in your textbook it also calls this an electron beam. So you basically have a beam of pure electrons. So by studying this beam of electrons, it allows us to study the nature and the characteristics of electrons itself. That's why it's such an important thing. That's why this discovery of the cathode ray of thermionic emission was such a huge thing, a huge part of our understanding of how electrons work. All right, so that is basically how the cathode ray works and what thermionic emissions are. Let's read some of the other explanations. So yeah, there are many free electrons in the metal wire, for example, tungsten filament. So when the 6 volts of DC power supply is switched on, the temperature of the tungsten filament will rise. So the tungsten filament will start to heat up, and the metal surface will start to heat up as well, and then the electrons will get sufficient kinetic energy. So like I was saying, when you add heat, you're adding kinetic energy to the free electrons, and now the electrons will now have enough energy to leave the surface of the metal plate and move. Now, this is why we use a glass vacuum tube. So in a glass vacuum tube, the electrons are able to accelerate towards the anode without colliding with air molecules. So meaning to say there is no resistance from the air. In some experiments, they use not a full vacuum. They use a tube that has some air in it just to study the effects. But when you use something that has air in it, what happens is that the electrons have to collide with the air molecules and there is energy loss. However, since the electrons are not colliding with air molecules in the vacuum, so there is no energy loss when we move from one side of the anode to the cathode. So meaning to say every single electron that gets released from the cathode ends up at the anode, and electrons move with the maximum velocity. Since none of the energy is being lost, all of the energy gets converted into its speed. So now when a vacuum tube is connected to an EHG power supply, the electrons emitted from the cathode will be attracted to the anode at a high velocity to form an electron beam. Yeah, so that was what I was just talking about, Okay, when you heat this up, when you connect it to the electricity, cathode heats up, releases electron, creates an electron beam that goes towards the anode. This high velocity electron beam is known as cathode ray. So sometimes you call this an electron beam, sometimes you call it a cathode ray because it comes from the cathode. Okay, so the electron beam will complete the EHT power supply circuit, and the milliammeter. Okay, so it's just an ammeter, but since we're dealing with smaller current, so milliammeter. A milliammeter will show that a current is flowing. So if you connect an ammeter, or in this case a milliammeter, you can see that there is current flowing in the circuit. Now here's something very interesting. If the connection of the EHT power supply is reversed, the milliammeter will not show any reading. So going back to our whiteboard, if I was to take these two ends, so now, let me just put my milliammeter. So this is our ME. So we have a milliammeter here. So if I were to now reverse the polarity of the battery, so instead of negative on this side and positive on this side, I'll do the opposite and put this negative and put this on positive. Now suddenly what happens is that we no longer have any electric current. The milliammeter does not show any reading, and there will be no electron beam. No, nothing. There will be no electron beam. Now, if you think about carefully, you should be able to figure out the reason why. It has to do with what I was explaining just now. All right. Now the tungsten filament, obviously, since the tungsten filament is here, it will still heat up. You know, this plate will still heat up, and because this plate will heat up and still end up being very hot, it will still release electrons. It will still release electrons, but these electrons will not go this way. No, will not happen. Why? Anyone wants to guess why? If you heard everything, or if you remember the property of an electron, then you know that you remember that electrons are negatively charged, right? So because this plate is negatively charged now, and this side is positively charged, what happens is now these electrons have no interest in going here. Right? These electrons are negative, and this side is also negative. Then the electrons are like, why should I go there? I'd rather be here, where the positive is. So that's why you cannot switch, or rather, in this, when this thing will not work if you were to switch the positive and negative sides. And then if we put it back, so that we have this is the negative side and this is the positive side, then we'll get our electron beam or our cathode rays. So this is something that's very important. So this means that this circuit here only works in one direction. Now that's something very interesting. And in electronics, that's something that's very important. Something that allows electricity to only move in one direction is very important in electronics. Why is that? I will tell you later. That's part of the later lessons. But just remember for now that if the connection of the EHT power supply is reversed, the milliammeter will not show any reading. Meaning to say there will not be any flow of current if you change the connections. So you have to have the right connections if you want your cathode ray to work properly. Okay. So effects of electric field and magnetic field on cathode rays. So this now has these are different experiments. Excuse me. These are different experiments that people have done to the electron beams. Excuse me. If you saw the video earlier, you know that the first guy to discover this, also did similar experiments. Excuse me. And it's through these experiments that we can discover discover some of the properties of this cathode ray. And by learning about the properties of cathode rays, we also learn about the properties of electron beams. So I'm not going to go too deep into these two experiments. I'm just going to show you the setup of the experiment, and I'm going to talk about the results and the conclusions. If you want to know more details about the experiments, I encourage you to check that out on your own. So cathode rays are beams of electrons moving at high speed in a vacuum. That's the important part. It's in a vacuum. The characteristics of cathode rays can be studied using a deflection tube and a Maltese cross tube. So these are the two different experiments. So activity 5.2 is using a deflection tube, and activity 5.3 is using a Maltese cross tube. So basically, I'm just going to explain this. So you have the cathode ray, right? You have the anode and the cathode. So just like what we did earlier. And now this anode here, there's a little hole in it to allow some of the electrons or some of the cathode rays to also go out to the end of the tube. This is 5.2 in your textbooks. And while the cathode rays are shooting out towards the end of this vacuum or this glass tube, it goes between two deflection plates. Now these deflection plates always come in a pair. And these two deflection plates also has its own circuit. So you have three circuits now. You have one circuit for the tungsten filament. You have one circuit for the cathode and anode of for the thermionic emission, and you have another circuit for the deflection plate. And so this deflection plate has a positive and negative side. And so when this thermionic ray or cathode ray shoot out, it goes between these two plates. Now these two plates are positively and negatively charged, right? And so what happens is, if whichever side the positive plate is, the cathode rays will tend to bend, will bend or will curve in whichever direction has the positive side. See? So since the positive side is up here, the cathode rays will bend up towards the positive side. If the positive side was below, it will do the opposite, where the cathode rays would bend towards the lower side. And so this is how we came to the conclusion that a cathode ray is negatively charged, because the cathode ray always seems to be attracted to where the positive charges are. It's always affected, or it's always attracted by positive charges. And so this is how they came to understand, oh, electrons have a negative charge. In fact, when they first discovered the electron, they did not call it electron at first. They actually called it sounds kind of weird, it's called a as in negative, a negatron. Right? I have to pronounce that carefully because it sounds like something else. They called it a negatron, but then afterwards they changed it to become electron. Megatron's brother. Yes, you have Megatron and his less famous brother Negatron. Oh, that's funny. Okay. Now, the other type of experiment that they did is using a Maltese cross. So basically, it's the same as the one just now. We have the cathode, we have the anode, and we are shooting out a cathode ray. And this time we're using a Maltese cross. We're blocking the path of the anode. Sorry, not the anode, the cathode rays. And here we have a fluorescent screen The fluorescent screen is just to show the cathode ray because actually I know in the picture it looks like there's a beam, but you can't actually see it unless you put a fluorescent screen. Then that fluorescent screen will allow you to see it. And what happens is you'll see that there'll be a shadow being cast on the fluorescent scene. So what are the conclusions that we can get from these two experiments? So the conclusions that we can get are: first, cathode ray travels in a straight line. How do we know that? Because when the cathode ray travels and it's blocked by a Maltese cross, it creates a shadow, and the shadow is in the same shape as the Maltese cross. So meaning to say the electrons travel straight. If the electrons could curve around, sort of, the shadow would not be so perfect. But because it's a perfect shadow, you can assume that the electrons travel in a straight line. Cathode rays can be deflected by an electric field, like what we saw earlier in this experiment. Cathode rays are negatively charged because they always tend to be attracted to any positive charges. And the last one is cathode rays possess momentum and they possess kinetic energy. Because when we shoot the cathode rays to the fluorescent screen actually starts to glow. So from that we can tell that there's energy. There's energy and there's momentum and there's kinetic energy from the cathode rays. So some very interesting things. So because of this, all of these things, and especially these two, cathode rays can be deflected by an electric field and cathode rays are negatively charged. All these things helped us to also understand what electrons are, because remember, cathode rays are basically an electron beam. You're basically shooting a ray of electrons. All right. Velocity of an electron in a cathode ray tube. So we've talked about the electrons and how the electrons move from one side to another in these cathode ray tube. And especially earlier, where was it? Here we go. I mentioned earlier that when the electrons move towards the anode, there is no energy loss. There is no energy loss because it's in a vacuum. There are no air molecules for it to collide with. Therefore, the electrons end up moving at maximum velocity. What is maximum velocity? Meaning to say, all the energy that those electrons have goes into its velocity. That becomes important here when we try to study the velocity of an electron in a cathode ray tube. So the the electrical potential energy of an electron, meaning to say, how much energy does this electron have? That's basically what we're saying. How much energy does an electron have? Or how much electrical potential energy is given by the formula big E equals small eV, where E equals the electrical potential energy in joules. So what the total electrical potential energy? E is the charge of an electron, which is this one. This is probably a number that you're gonna have to memorize. So take that out. So charge of an electron is 1.6 times 10 power of negative 19 coulombs. And V is the potential difference between the cathode and the anode of the EHT power supply. So what's the voltage? So again, this is the picture. We have the vacuum, so the vacuum tube. We have the cathodes and we have the anodes. And the electrons move at maximum velocity towards the anode. Okay, that's what we saw earlier. So when the EHT power supply is turned on, electrons are attracted by the positively charged molecules. And as there are no air molecules in the vacuum tube, electrons will accelerate to the anode without any collision. This is the important statement here. The electrons will achieve maximum velocity, Vmax, when they reach the anode. So, because they reach maximum velocity, we can use the principle of conservation of energy. Right? So, in the principle of conservation of energy, we learn Newton's laws. For every action, there's an equal and opposite reaction, right? The electrical potential energy will equal the maximum kinetic energy. Okay, so in other words, EV, the formula given is EV equals 1/2 mv square max. So I want to talk a little bit about this idea here. Electrical potential energy equals maximum kinetic energy. Meaning to say, all of the electrical potential energy, every single one of it, gets turned into kinetic energy. Alright? This is something that, by the way, this is rare in physics, okay? Usually there's always some energy being lost somewhere, either as heat or as either as heat or as because of drag, it has to fight air resistance. But in this situation, all of the electrical potential energy gets converted into kinetic energy. So if you know how much electrical potential energy you have in the beginning, then you know how much kinetic energy you'll have at the end, basically. That's why we are able to use this formula of the electrical potential energy in the beginning will end up to be equal to the maximum kinetic energy. So once you know how much the maximum kinetic energy is, you're able to calculate the maximum velocity. So formula EV, the first formula that we learned just now, equals to 1/2 mv square max, where E equals charge of an electron. So small letter E equals charge of an electron. Capital letter V is the potential difference between cathode and anode, so how many volts. M is mass of an electron, and V max, this should be small letter V, I'm sorry, is the maximum velocity of an electron. And you also need to remember these numbers. So the charge of an electron, we talked about that just now, is 1.6 times 10 power of negative 19 coulombs, and the mass of an electron is 9.11 times 10 negative 31 kilograms. In other words, very, very light. Very small. Sorry, I was blocking that. So make sure to try your best to memorize these two numbers, because I'm not sure if they'll give this during the exam. There's a chance they won't. So remember this. Remember the charge of an electron, 1.6 times 10 negative 19 coulombs. And remember the mass of the electrons, 9.11 times 10 negative 31 kilograms. So once you know these two things and you know this formula, then you can start solving questions. So, example question. And then later you can try to do your own examples after this. So example 1. So figure 5.5 shows an electron beam that is accelerated from the cathode to the anode in a vacuum. So just like what we are talking about. Remember that when I say there is no loss in speed, that only applies when it is a vacuum. If the question is not in a vacuum, then it will not achieve maximum velocity, because there is some loss of energy due to having to fight the drag or having to collide with the air molecules. So only in a vacuum do you achieve maximum velocity. Oh, sorry, not yet. So the potential difference across the cathode and the anode is 550 volts. So already stated in the question. So in this example, everything is already stated. So mass of the electron, charge of an electron is given, and the voltage, which is not the voltage, but the potential difference, which is 550 volts. So if we were to write on a whiteboard all the information that we have, well, first, actually, let's read the questions first. Sorry. So this is the setup that we have. Now let's look at the questions. So first question is, what is the electrical potential energy of an electron? Okay, so we'll look at these questions one by one. And next is, what is the kinetic energy of an electron when it reaches the anode? Second question. And the third question is, what is the maximum velocity of an electron when it reaches the anode? So 3 questions, A, B, and C. So let's take a look at the information that you already have. I'm going to write this down on the whiteboard. So potential difference across the anode and cathode is 550. So V equals 550 volts. Okay, charge of an electron doesn't change. Okay, so 1.6 times 10 power of negative 19 coulombs. And the mass of the electron, or M, small letter m, is 9.11 times 10 power of negative 31 kilograms. So this is all the information you need to answer the questions. Alright, so question number 1 is asking, what is the electrical potential energy of an electron? So what is the formula for electrical potential energy? We saw it earlier. So formula for that would be, question A, electrical potential energy is capital E. Capital E equals small letter e times the voltage. Okay, so just put all the information in the question. So 1.6 times 10 negative 19 times 550 volts. You get a total of, it's all in your textbook, you get a total of 8.8 times 10 power of negative 17 joules. So that is the potential energy that you get for this question, right? I actually already wrote all the solutions in the slides as well, so you can check that out as well, and it's in your textbooks anyway. So this is the amount of potential energy of an electron. Right, let's look at question B. So question B is, what is the kinetic energy of an electron when it reaches at the anode? Now for this, it's easy. Remember that we use the principle of conservation of energy, where electrons receive maximum velocity and there is no energy loss. I forgot to write that there. There is no energy loss when you reach the anode. So meaning to say, if there is no energy lost, all of the electrical potential energy in the beginning gets converted to kinetic energy. So we don't have to calculate actually. So we just need to apply principle of conservation of energy. Conservation of energy. So kinetic energy gained will equal to the electrical potential energy. Alright, so electrical potential energy. So we already calculated in the last question how much is that electrical potential energy. 8.8 times 10 power of negative 17. So 8.8 times 10. So it's going to be the same. Alright. Basically think of it like this. In a vacuum, right? When it's in that vacuum, when those electrons move, the potential energy of the vacuum, it doesn't have anywhere to go. It's not going to go anywhere else because it's in a vacuum. It's only going to go to the anode. So all the energy ends up turning into kinetic energy and goes to the anode. That's why the potential energy and the kinetic energy gained is going to be the same. You cannot gain more kinetic energy than the energy that is given to you. So since this is the amount of energy you're given in the beginning, then you end up with the same amount of energy. You cannot gain and you do not lose any energy. All right, and now finally the last question. Last question is, what is the maximum velocity of an electron when it reaches the anode? So how fast now does this, how fast does this electron go? What's the speed that it reaches? And what formula can we use to calculate this? So again, back to the whiteboard. So we studied the formula. We used the formula 1 over 2 m v square max. So max meaning to say maximum velocity equals to EV. Okay, based on the conservation of principle of conservation of energy. So if we just rearrange the formula, we would end up with V max equals square root 2 EV over m. Alright, so just use all the values that we have learned already. 2 times E equals 8.8 times E equals times 8.8 times 10 negative 17 times V voltage, so times 550 divided by M, which is again the mass of an electron. We know that mass of an electron is 9.11 times 10 power of negative 31. Alright, and you get your final answer to be 1.39 times 10⁷ meters per second. So actually that's pretty fast. So that's how you do the calculations. Basically, all the information earlier was already in the it's already in the question. Okay. There's a little bit of mistake in these slides. So, but the one I did on the whiteboard is correct. So, when I send you the slides, I'll correct the slides before I send it to you later. So don't worry about that. Okay. Now, so that is basically the end of the topic of topic 5.1. I'm gonna give you some assignment, but before that, we still have some time. I wanna go just a little bit into topic 5.2 because the topic 5.2 has a little bit of a connection with what we were learning earlier. All right, so 5.2 semiconductor diode. So semiconductor diode. So now we're getting into electronics, like how computers and electronics, such as any electronic devices that you use, computers, speakers, radios, any other electronics that you use, how these things work. And a very important thing in the way these things work is what we call a semiconductor diode. So what is a semiconductor diode? Well, we know what a semiconductor is. So we know that a semiconductor is something that is somewhere in between a conductor and an insulator. It's not fully a conductor because it doesn't always necessarily just let electricity flow through it, but it's not fully an insulator. It does conduct electricity, but only under certain conditions. All right? It's kind of like ada syarat dia lah. You have to give certain conditions. Once you fulfill these conditions, once kamu sudah penuhi syarat-syarat dia, baru dia kasih limpas kau. Baru dia kasih limpas itu current. You can imagine a semiconductor as like a gate man. Okay, a security guard that stands at the gate, the gatekeeper. And every time electricity tries to go through, he says, "You shall not pass. Unless you fulfill certain requirements, then he'll say, okay, now you may pass." Now, the other thing is a diode. Now, what is a diode? Well, actually, the thing that we'll take a look at earlier this thing here. This is actually a type of diode. All right? Remember what I told you? I told you that if you change the direction of the flow of electrons, meaning to say I switch the negative and positive side, right? Then if I change it, then suddenly there is no current. In other words, current can only move in one direction in this particular circuit that I have here because of the way that thermionic emission works. So this is actually what a diode does. So a diode So a diode is an electric component that allows which allows electric current to flow in one direction only. So if I were to take a battery, it would only work in one direction. If I were to turn around the battery, suddenly it doesn't work anymore because of the diode. The diode only lets the electricity flow in one direction. Just like the thermionic, the cathode ray tube that we saw earlier. That's why actually there are different types of diodes. Your textbook says that a semiconductor diode is an electric component which allows electric current to flow in one direction. There are other types of diodes that also do the same thing. One of the other types of diodes that we have is what we call a thermionic diode, which uses what we were just studying earlier. So a thermionic diode, why would you need a diode? Why would you need something that allows electric current to flow in one direction only? Well, the reason you want a diode is because of something called this, AC, alternating current. So you have learned that transmission of electrical power to consumers through a network is in the form of alternating current. So we learned before that, you know, those big cables that are sending electricity to houses all over the place, those big cable wires that you see, these are using alternating current, where the direction of the current actually alternates. However, in everyday life, many electrical devices can only function with direct current, meaning to say current that flows in one direction. Right? Because think about it. Imagine you're trying to use a fan. Right? So a fan turns in one direction. So you use a direct current to turn it in one direction. If you try to use alternating current, then you'd end up with a useless fan that turns left and right. It keeps switching direction and never really blows the air properly. That's why you use direct current. So many electrical devices, I would say most of it, can only function with direct current. So in order to use direct current in your house, you need a way to convert alternating current into direct current. That's where the diode comes in. So since a diode only allows electricity to go in one direction, basically it's a way for us to force this alternating current to stop changing directions and make up its mind to move in only one direction. Basically, it's like once you go through, you can't go back. Alright, so it converts the energy from alternating current to direct current. Alright. I'm not going to go any further than that. That's your introduction for semiconductor diode. We actually studied about a diode earlier, which is a thermionic diode. Alright. So, any questions before I let you go off to do your assignment for this week, or for today actually? So yeah, so that's basically topic 5.1 and a little bit of 5.2. So when we go into diodes and transistors, diode and transistors are very closely related. So So I don't want to rush through the diode part. That's why I'm only giving the introduction for diodes today. No questions? Everything clear? It's a little bit on the theoretical side today. Very interesting, but especially when you think about a beam of pure electrons. For those of you who might be wondering what the use of a cathode ray would be, there are a few things. One is, like I was mentioning, the study of electrons. Since it's basically a beam of electron, we can use it. It's a chance for us to study the properties and the nature of electrons. That's one of the first uses. The other use is we use cathode rays, or not just the cathode rays, but the electron beam. One that I found out is in welding. So this electron beam also has the potential to carry a lot of heat, and you could use it actually to do welding. The other one is in old televisions. So televisions nowadays don't use this technology, but most of you guys probably remember those big old televisions, those like thick ones. Nowadays televisions are like really thin, but when I was a kid, almost all televisions were actually thicker than the screen. So if the screen is this wide, then the back of the television is even thicker than that. That's because in the inside of those televisions, we actually have a cathode ray tube, believe it or not. And it uses the cathode ray to produce the picture in front. So that's old technology. Not very common nowadays, but some people still like to use those old televisions, especially for certain hobbies. There are people who still like to use what's called a CRT, cathode ray tube television. But other than that, nobody really uses those kinds of televisions anymore. Okay, so if there are no further follow-up questions, I need to take note of. Okay, so if there are no further follow-up questions, then you may proceed to doing formative practice 5.1. All right, and then once you're done, you may submit the work and you can do the correction. You can check for the answers at the back of there's a link at the back of your textbook for the answers. If you need the answers or you can't access the web link, you can ask me. I have a copy of the answers as well on my computer. Okay, so I'm ending this Google Meet unless you have other questions. So if you have no other questions to ask, then you may leave and continue with your work. So thank you everyone for listening. Thank you for coming to class. Have a nice day.